Hello and welcome to Advanced Data Analytics. I'm Jun Lee. In today's class, this is a video lecture. In the first week's study, we first recap some of the most essential concepts in data analytics. Particularly, we would like to review some of the important understanding of data and have a comprehensive understanding of the whole picture, that what it is meant to do data analytics, how to extract information from data, and why and how can we use information from data to do predictive tasks. Then we will discuss our first data model in this semester. Arguably, that could be the simplest model possible. It is a linear model we just directly access the data attributes and combine them together to do predictive tasks. We will consider the model, how to use it, and how to train it given data and its properties. Especially, we consider consider deeper of the training details of the algorithm. Later in this video, I will discuss the tasks we will encounter in the first week's lab tutorial. We will get familiarized with the programming environment and the machine learning and data analytic software packages we will utilize throughout this semester. Look, this mind-blowing diagram explains the idea of learning from data to do future predictive tasks. Please do not try to memorize and try to guess every element in the diagram. Keep it as a reference. We might revisit the concept here from time to time. Okay, first let's have a look at a much simplified version of the learning diagram. Now consider a problem of classifying animals according to a limited observation of their images, such as the silhouette of the shape of the animals. We would like to classify the animal into three classes: birds, mammals, and fish. In this question, obviously, the data are the shapes of the animals. To frame the problem as a learning problem, in the stage of learning, actually, a learner will accept two parts of the data. The first part is the observation, that is the shapes of the animals, the images of the shapes. And the second part is the learning target, so that the learner can learn anything from the shapes. That is the ground truth labels for those shapes. In this example, I give several images of the birds and of the mammals and of the fishes, and we can see some tendency of how those animals shaped, of course. And in the deployment stage, that means when you put the model into actual use, the model can only access to the observation mode, of the data, that is the shapes, these images. And for the classes, the labels, the model needs to predict for itself. Of course, that is the way the model to be useful. Apart from the data, to define a learning problem, we need to decide the range of how we consider as a model or as a predictor. For example, in this problem of classifying animal shapes, we may consider to first observe or extract the body part from the shapes and classify um, the, uh, the animals according to the body parts. This could be a good strategy, could be bad one. Of course, obviously, if you actually apply this strategy, you will face another kind of problem of how to extract the body parts. Okay, but good or bad, we can put it on table and consider these possible classifiers or models or predictors. And another thought may be we can look at the shapes and from our memory to consider previous observations in which kind of environment such creatures could be observed. Well, such associative solution might be actually used by wild animals. Who knows? That might be useful for their survival. And if you take it from a Baba's view, you may end up with only two kinds of things, eatable and non-eatable. Silly or smart, stable or fragile, we consider all kinds of different predictive agents. We call them analyzer, predictor, model, gambler, guesser. We have a name for all those. They are hypotheses. And all possible hypotheses within consideration, we call them hypothesis space. And learning is a process. In face of the data, to choose a good hypothesis that minimize the risk of making mistakes in the given data set, or maximize the reward you can obtain from the data set. And after learning, you will end up with one single hypothesis. You will use this hypothesis to deal with future observations. And the essential challenge in the learning diagram is that it is only the performance in the future observations that matters for the learning, for the chosen hypothesis. But obviously, the future observations has not been seen at the time of training. Let us consider those learning framework elements and their relationships. The first one is, of course, data. From previous study or from common sense, everyday common sense, data is the quantifiable, observable part of the problem of interest. A quite relevant concept of data to our study is that of a data space. So what is a data space? Consider that each data sample has several attributes that we can put into numbers. So in our analytics, we use multiple numbers, a certain number of numbers to represent a data sample. If we consider such numbers the coordinate of a point of some high-dimensional space, we can have a geometric view of the entire population of the data. That is, the population live in the corresponding space. Put into this way, this almost sounds like tautology. Okay, we have n attributes to represent some data sample, and if we consider the attributes as coordinates, now we have a sample as an n-dimensional point in an n-dimensional space. But what we can get from such a different view of the same thing. Firstly, a geometric view is more intuitive for us to understand the data, and especially beneficial to the beginners of data analytics is that it helps you to understand the different technical terms related to the model. For example, today we will learn about linear model. Put it simply, it is just to give a weight to each of the attributes, and the weight keeps constant during the entire analytics. And such a model is called a linear model. Now, why it is called a linear? If you understand the data as a population in a space, such a model is actually draw a line or a flat surface inside the space. So it is called linear. Secondly, beginners or even experts often have a mind frame about analytics. That is, we discriminatively view the different elements in the learning framework. Generally, people think data is the first citizen in the framework. That is reasonable and natural. Think about that. Data is, well, it looks and it feels more real than the learning algorithm or the models, because data are there, they are closer to and they reflect the reality. And the hypothesis space, of course, from its name, is hypothetic, and the learning algorithm is the kind of a mechanism to choose from this hypothetic space. But on the other hand, in practical analytics, the reality must be observed and represented in some way. And this transformation from the reality to manageable, analyzable object is closely related to the analytic method of your choice and how you design your strategy of tackling the problem. For example, in the animal shape image classification problem, there are different ways to represent a shape image into a few numbers as the data sample for analytics for classification. One possibility is to count the feet of the animal. Now you can represent different animal shapes into those have 0 feet, have 2 feet, have 4. In this way, at least we can represent a shape into a number that is manageable, but sometimes it's not very much informative. Another possibility is to try to find the mouse area on the shape and to measure how curved the mouse is. Like in the mammals, the mouse is more smoother, and in fish, the mouse area is sharper than those of the mammals, and in bird's beak, it is very sharp, and this sharpness of a mouse can be another measure. Of course, you can combine these two different measures together and have a two-dimensional representation of the data. The importance of the form of data is that it is closely related and sometimes determines what kind of model or predictors we may use in our analytics. In the above example, if we represent those shapes in one number, be the number of feet or the sharpness of the mouse, and using such representation, if we want to build any classifier, the only thing we can do is to threshold that number and using that threshold to differentiate different kind of animals. But if we build a two-dimensional representation of the data and put the data in a two-dimensional space, now we can use a more sophisticated model to have some boundary in the two-dimensional space to classify those animals. The third point I want to talk about data space is that the concept of space may be more general than you might think of. The space and the points in it is not always explicitly represented as a certain number of real numbers. For example, consider the procedure we human beings recognize the image of some known creatures. When we see an image, generally we do not disintegrate the image into some specific numeric measurements. On the contrary, from memory we may retrieve some other forms of the creature that is closely is similar to the one that has been observed. It is the similarity we rely on to classify and recognize the new observations. In this aspect, as long as we can establish the measurement of similarity or dissimilarity, we may be able to perform effective data analytics. We will talk more about the measure of similarity and inexplicit representation of data space, and how to use them as to develop analytic methods later in this course. You can go to UTS Online. In our subject, it's here, Subject Documents. If you click here and find Lab Materials 2017 and go to Lab 1, and please locate our data here. That is called usps.train.txt. Download it. If you click it, oh well, you have the text file. I don't know what is in your browser, but my browser just opened the text file. In this case, you can use Save As in your browser. I will click Command S or Control S if you are using a Windows computer, and you can save this usps.train to your computer. A good way to save it is go to your home directory. If you use Apple computer, the username should show here, and that means that is your home. And I will create a new folder. Let us call Advanced Data Analytics 2017, and in this new folder, create another one for the first week. Okay. Save this file here. Yes. Otherwise, your browser may just download that file. In that case, you may follow the previous procedure of creating a specified folder for this week's experiment and move downloaded file into the folder. After we have downloaded the file, okay, I think I needed to talk about a little bit about what the file is. Each row in the file contains 256 numbers, and each of the numbers represent the brightness of a pixel in a 16 by 16 image, and each of the image is a handwritten digit. The task is to classify what the digit is using this 256 dimension representation of the image. We will build a linear model to classify these images, but the dimension of the data, which is the 256, is too much for our model. As we have just discussed, the representation matters for our analytics. So we start with processing the data in a simplified form. Following downloading the data, Let us open a terminal. As I have introduced in the welcome video, now you should be familiar with this procedure. In this terminal, now this little tutor here means now we are at the your home directory. Let's have a look. That is me, Junli, and in the users. That is the reason why we create a specified folder from the home directory, which makes life easier for us. I will change direction into the one I have created just now, ADA 2017. Okay, and CD into the subfolder week 1. If I type list ls, we'll see the data file is there. As we have learned in the welcome week induction week, now we can launch Python notebook from this directory. I would like you to launch the Python notebook in the directory and talk about directory so much, because if you look at your data file and the working directory of your notebook together, that will make life easier for you when you are programming your Python code to load the file. You do not need to specify the full path to the file, which may create errors. Especially sometimes the way to specify the paths is different from Windows computer to Linux computer. But anyway, if they are in the same directory, you just need to use the file name to specify the file. Now we launch the Jupyter Notebook. That is create a new notebook to do the data transformation. If you click here, new, it will allow you to choose what kind of a file to create. We need to create notebooks. I have a different kind of Pythons, but I think you will have only one, and click the only one Python file, and it will create a new notebook for you. It's called Untitled. You can name it, for example, my experiment. Okay. As we discussed, we will use the numeric Python package for processing most of the data. So first, let us import the package. Name NumPy, numeric Python is MP. That is for easy typing. Click here to execute it, and now we have the NumPy package in ready for use. We can try by typing numpy.version. When you are doing your typing, if you know the first few letters of what you are looking for, after type the first few letters, you can hit the tab K, T-A-B-K on your keyboard. The environment will automatically complete the command for you. So programming isn't as tedious as it seems to be. Now let's execute this one. Now I have a Python here, right? So version number might be different from my computer to your computer, but we will only use the basic functions, so it won't matter very much. Okay, now we have our Python, and we also employ magic in this notebook. Note the command start from the percentage sample isn't the part of Python language, but it's the convenience provided by the notebook. This one will allow you to conveniently use graphical plotting functions that provides us intuitive exploration of the data. execute this, and the output might be different from your computer as well, because it will the notebook will employ some backend graphical function for you. Doesn't matter here. After these two commands, we are ready to handle our data. So the first step is, of course, to load the raw data from the file. The command we will use is one provided by the NAPI package. Let us create a variable to store the raw data. Let's call it raw data, of course. And the command, the function in Python is named generate means generate Python array from text, because our data file is a comma separated plain text file. If you don't know how to use this command, you can hit the you can have this pair of parentheses and move your cursor within this parentheses, and now the notebook understands that you are trying to get some you are now going to fill information to use this function, and it can provide you help. If you want, you can hit Shift plus tab, the tab we just talked before. It brings the document of this function and tell you how to provide necessary information. Look in this function. Actually, the only essential information it needs is this one, file name. It needs the name of the text file from which you want to load the data. For all the others, additional or auxiliary information it will use to process the data. But because our data format is pretty standard, so we do not need to use those opinions here. And if you leave it there, the parameters of the function followed by this equal symbol means it has a default value with it. So we don't need to worry about that. And now the only thing we need to do is to fill the file name here. And if this information is too few for you, you want something more, you can click this plus symbol here. It will bring the full document of the function for you. And of course, if you still feel not unsure about how to use the function, you can Google this function name. Let's put our file name here, and our file is called usps.chain.txt. Okay, let's execute this cell. It takes a little while. When the cell is being executed, there is a small star sign here. After it's being done, there will be a number here represent the order. The order, that means from starting of this experiment session, what is this command in the line is. Now this is the fourth command we execute. Now we have 3 cells, but remember we have experiment with the NAPI version, so this is the fourth command we have executed. And because Notebook provides you a nonlinear way of execute programs, so this numbers is sometimes quite helpful. Now we have the raw data loaded. Let's have a look at the basic information of the raw data. We can print the type of this variable to see if it is actually a NAPI array. Raw data. Look what it is. Yes, this is a NAPI n-dimensional array. But how many dimensions it has and what is the exact shape or the dimension of the array, we can use the information called print raw data. Remember this, the auto completion. Now I have two variables starting with raw. Oh, I don't know when I get the raw input, but anyway. Oh yeah, raw input is a command of Python. We can choose raw data here, and now if I click the dot, it will, because this is an object, it has several methods coming with it. And if I hit this dot, I can use different methods. And this method, particular method or attribute I want to bring up is about its dimension now. But for example, if I forget what I need to do, I click the tab again, well, it will bring all available callable functions and attributes of this object. The one actually I want to use is called shape. Yes, it comes out, and let's have a look. Oh, now this is our data shape. It has 7,291 samples, and for each of the sample, it has 257 numbers in it. Why it is 257 instead of what we have talked, 256? Can you guess for a while? Okay, the answer is, now let's have a look at one particular sample. For example, if we take the first sample, we can call it 0. But if I execute this command now, it will bring me 257 numbers. And let's have a look. It looks like the first guy here is the class of the digit. It is a digit 6, and the others looks like the brightness or the darkness of the pixels in the image. If that is the case, we would expect each sample would be in the same format with an integer in the first place and followed by 256 float numbers from the smallest -1 to the largest highest value +1. Okay, we can verify our guess. One way to do that is to investigate the first few samples. The first sample is 0, okay, and in this way we need to look at too many numbers. Let's say if I only want to see the first number of a sample to verify if this number does represent the class of a sample. This way of indexing it means I take the first element from the first sample, and we can simplify this using a comma to separate these two subscripts. Okay, now I will expect 6, right? And how about to have a look at more than one sample? Okay, we will have a look at the first number of the first 10 samples. You can use the column to represent from 2, okay, from 0 to 10, not including 10, but it will bring us 10 samples. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not including 10. Okay, have a look at this. Oh, it seems that our guess is correct. This first element of each sample do represent the sample class. Okay. The next reasonable thing to do is to separate the data labels with the content of these images. So we can separate them, so we can use them separately in different parts in our learning algorithm. To do this, and we now know the first element of a data sample is a label, and the others are the contents. So let us say y represents the label, and let it to be raw data, and all the samples. Remember the column. The column sample represent the primitive of from something to something. If you just type the column, it will cleverly understand it as take all the possible values in the from to. That means from the beginning to the end. And let it take the first element. This instruction means you go from the first sample to the last one, and from each one you take the first element. After that, we would expect y to be this 7,291 labels of each of this sample. Let's verify it a little bit. Print y's shape, and for example, the first 10 elements of y. If remember that if you want to print the first 10 elements, you go from the 0th to the 10th, not including 10. But the column sample is smart. It can infer that if you do not provide it information, it will fill it a necessary one. So you can just type 10 and it will automatically understand you would like to start from 0. Let's have a look. Yeah, the shape is 7,000 something. Notice that this shape has only one dimension in it. There are 7,000 something samples, but in each sample there is no dimension that has length 1. This is only a 7,000 something vector, a list of numbers, and the first 10 numbers are here. Okay. Now we can using the same logic to extract the content of the data. Let x to be raw data. Okay. Also take from every sample, but exclude the first element. How to exclude the first element? If you express this idea explicitly, that means go from the second element until the last one. And we also need to use the column sample. And remember that it is smart, so we do not need to explicitly tell it the last one, which is the last one. We just need to tell it we need to go from the second one. And remember, the indexing in Python is starting from 0. So the first sample, the first element corresponding to the subscript 0, and the second one corresponding to the subscript 1. In this case, we will have the content of those images. Let's also check what we got after this manipulation. But probably we don't want to print the entire content of each pixels of an image. Let's have a look. That is good. But how can we check the image? We need some intuitive idea of the data, right? Okay, now let's have a look at it. The image, as we have discussed, is a 16 by 16 pixel image. And here the 16 by 16 pixel have been flattened or have been squished into this 256 element. One way to resemble the image is to let the array to be viewed from a different perspective, to let it to be viewed as a 16 by 16 array. You can use a command called reshape to do this. But first, let us take a single sample for this examination. Consider that x1 as a temporary variable. It is not a very good way to name a variable this way. If you have an x and you don't know how to name something about x, and just take the x1. Look, when you name your variables, think about maybe in 6 months' time, a future yourself. Look back to the code. This is probably not a good one, just for a quick glance of the data. Okay, let x1 to be the first image. For that, we can take the first sample from this x, and from the first sample we can take everything. And if you take everything from the first sample, you can just ignore this. Note, this is different from to take the first element of every sample. In that case, you need to explicitly specify you need every sample. But when you consider only the first sample and take every element of the sample, you can ignore this. Simply put, that is, you can ignore the tailing from everything to everything, but you cannot ignore the head from everything to everything. Okay. This is the first symbol, and we want a different view of that. What it is, we want to be reshaped into 16 by 16. Okay, but look, this won't work. Why? Look back at the shapes. This, for example, each shape is 2 numbers included in a pair of parentheses. Okay, even the shape is a trivial single number, it needs to be included in a pair of parentheses. That is, a shape itself a collective data type. It is not an integer, because an integer cannot cannot specify any kind of shape. You need a couple of integers, and those couple are called tuples in Python, and a shape is a tuple. So we need the 16 by 16 to be included in a pair of parentheses. Okay, let's have a look what we get of x1. Oh, we can just print x1's shape. Print out the shape of an array is a good inspection of any NiP array. Let's look at this. Good. And let us have a more intuitive look at this, a literal look. If you remember from above, we have populated our memory with functions provided by this magic. Note, this is not the standard Python command. It is provided for convenience in the notebook. But now we have the function from a particular Python package called matplotlib. You don't need to worry about this for now. We will learn about that in our lab tutorials. Now we can show images, and the function for showing images is not surprisingly called image show. We can show the image of x1. See what we will get. Execute. Oh, good. That is a 6. Remember the label of the first element? 6, right? Okay. Where is my 6? Don't worry about that. But that 6 looks very pretty. One reason is because you have only a 16 by 16 image, and to show something that is visible to you, the image must be enlarged, and the rendering environment, a rendering function in the environment automatically do some smoothing, interpolation, image processing stuff for you. But actually, for inspecting data, probably you don't want to it to perform such function for you. So you can give it an option, and that option that by default it's smoothing, and now you are not using the default value. Remember, if you do not use the default value, you need to explicitly tell it using such mechanism, interpolation, let it to be nearest. That means whenever you want to fill a pixel on screen, find the nearest possible data value. Do not do any interpolation. And the color map, that means to interpret the one real number into some colors on screen. Do not interpret it as a pretty display for me. I just need the grayscale. I just want to see how dark, how bright a pixel is. So let it called gray. See what we will have. Oh, we still need to find the picture. Now, yeah. This one is one data sample. And now we are considering how to represent this data sample into a simplified form, and how to build classifiers to distinguish one sample from another and predict the scrapped label for the sample. Data simplification has anything to do with the task in our hand. In this particular task of classifying handwritten digits images, we may consider the one obvious property of an image we may consider is the average brightness. See, because different digits has different complexity in when you using pen strokes to write them. Some digits involve more strokes than the others, so each pen stroke changes the entire brightness of the image. So the average brightness can be one sign of what the digits belong to. And secondly, we can consider how the digit is symmetric in the horizontal way. For example, if we consider distinguish ones from fives, the ones could be quite similar from the left hand side to the right hand side, but for fives they could be quite different. So anyway, we just use these two properties as an example and show how the data preprocessing and model building works. Let's consider a sample X. Look, if the sample is, let's delete this particular sample and consider a general case. Now we have 7,000 something samples. If for the sample we need to consider let it to be X something. Okay, if that is a sample of interest, let us do first its mean value, and this is easier. Let's give it a variable name, call it U. Let U to be the sample of interest, and the symmetric value, got its mean value of the brightness in U. We can simply take U dot mean and call it feature 1. Okay, and for the for the horizontal symmetric property, we need to first represent U in a 16 by 16 image. that is called U image, because a different view of U reshape 16 by 16. And we have a horizontally flipped version of U image horizontally flipped. Let it to be U image. Now U image is 16 by 16. If we want to horizontally flip it, we want for every row of the image. For every row, we use the column here, means from the first row to the end. And to flip it, let us to represent this into an instruction primitive, that from to primitive, that is from the end to the beginning, and use -1 as the increment of your index. So from the end, how to represent that? That could be 16, and to the beginning, that could be 0, and let us use -1. Okay, but this won't going to work. Remember that this from is inclusive. If you put 16 here, the indexing will start from 16. But as we have learned that Python uses 0 starting index, so if you have 16 elements, the last one should be 15. And the from to, the to part of the primitive is exclusive, so it won't get into 0. It will get one element, one index before 0. That could be 1, but we actually want it to go to 0, so this should be -1. And the third argument of this primitive is the step. We are going to increase the index by -1 or decreased by 1 in each step. Also remember one thing is, if you do not specify the from and the to, the column operator will smartly infer that for you. So actually we can save this and save this. Only use the column -1, this magic, to index an array from the end to the beginning. Let us, before we put this into work, let us do an experiment of this kind of complex indexing first. Say let A to be a list, maybe 1, 4, 9, 16, so square of integers, and let us print A and print inverted A. What we get? Look, it works. So in this way, we flip the columns in each of the rows. Okay, now we have U image from U and horizontally flipped version of that image, and we can look at the difference between these two images, and the difference is not surprisingly, take that using the linear sample to represent, take the difference between these two, H flip, yes. Now this is the difference, but actually we would like to take the absolute value of this difference, okay? And the absolute value is represented by np.abs. This would be another 16 by 16 array, and each element would be the absolute value of the difference between the image version of this symbol and the horizontally flipped image of this symbol. And from this array, we can take the mean value of those absolute values, and that will be our second feature. Let's have a look. Execute this one and print feature 1 and feature 2. Well, looks like two reasonable numbers, but obviously to put things in a context, we need to calculate a lot of such features, right? Okay. To perform this operation for all the samples, let us write a function for that. Define extract features for a sample X, we can simply copy and paste this. Remember, Python infers the structure of the code using indentation. So we need to indent this part to show that this code block belongs to this function. Also, let us call the argument to be u. So we do not need to change anything within this function. And let us to return these two features. Okay, now we are almost done. Let's define it. Nothing happens. That is totally normal. But in memory, we now have registered all those operations under this name of extract feature. Let us use this, apply this to the first symbol of X. Okay. Extract feature of the first symbol of X. What we will get? Pretty similar value. It is okay. So the next step is to apply this function to every single sample in X. But in this example, to further simplify the question, instead of classifying all the 10 classes of different 0 to 9 digits, we consider each pair of them together. As we have just discussed, let's consider to distinguish ones from fives for the moment. Now we need to extract the features of the ones and of those fives. To do this, let us create two containers of our data. Call that y15. Okay, let it to be an empty list, and there is X feature 15. Let it to be empty as well. Now we can go through every single sample in the data set. That's for this temporary Y and temporary X. In every Y and X. How to do this? Remember this zip function of Python. It is like, yes, for its namesake, like a zip. They put two lists together. When you do the for loop, it takes one element from each of the list in the zips input and name this particular element of this two lists to be Y and S respectively. And so the two lists to be iterated should be Y and our x. Remember that a Napier array can serve as a list. It allows you to iterate from its first dimension. For y, which is 7,000 times a list array, it can be treated as the 7,291 a long list, and for x would be treated as a list of the same number of rows as y's element, and in each of the row contains the 256 element of an image. So let's do this for loop, and we consider 1s and 5s only. So let's say if the particular y in our interest cases 1 and 5, what we will do, we let y 1 and 5 append this particular y, and let x feature 1, 5 append this particular x. But note, we do not want to append this 256 numbers. Instead, we would like to append a pre-processed version of that. That is, extract feature from this x. Okay. This is what we do. Look. Okay. We can now have a look at our data. So let's do a scatter plot. Say we have a scatter. Oh, after the construction of these two lists, both y and x will be a list of the samples and the samples features. We want to transform them into Napier arrays so we can manipulate them as matrix of numbers, and that will make it easier for us. So let us do this. 1, 5 is y1, 5 napi.s array, and x feet 1, 5. Let it to be napi s array. Execute this. Okay, let's do scatterplot. For each of the sample, we take its feature and take its first element, the first feature, and then for each of the sample, we take its second element. See how it distributes. Let's execute this. Wow, it looks like we have two groups of sample, right? Let's be more sure about that. We can scatter twice, and I remember we can specify the color of these samples. Let's use Y to represent its color. See what we will get. Oh, that is too small. Let me have a look. Because the third argument represents its size instead of its color. And for color, you need to use the argument called say. Okay, let's write this here. Wow, this time it works. it seems that our particular feature works reasonably well. Look, I don't know which color represents which, but this distribution of the data seems to distinguish one group of digits from the other group. For this group, almost all the blue ones, and this group are mostly the red ones. Okay. So the next step is to build data models to distinguish these two groups of digits. What we will do, we will use a particular linear model called a perceptron. That is one of the simplest model, and we will introduce this model in class. For now, let us show how easily we can implement such a model without understanding how it works. Okay, the package we will use is called scikit-learn. It's a scientific learning package for Python. If you have installed Anaconda, it installed with Anaconda for you. So you don't need to do anything. You can execute the following import instruction here. Scikit-learn. Yeah. Right. Let us execute here. Now we have scikit-learn package ready, and the perceptron model is in scikit-learn.linear. Oh well, my fault. You need to import its submodule within the scikit-learn. Yes. Okay. Depending on the organization, some packages, when you import the main name of the package, it import everything for you. But sometimes the package want to have more efficient use of your memory and computing source. When you import the package, it only import the core functions for you, and you can import the submodules in this way. Named submodule, which separate, you have to use a dot to separate submodule with the main name of the module. Now we can have a look at what we got in the linear module. Wow, we have a lot range of different models here ready for you. If you have used any other machine learning packages such as 9, some of our students have used in last semester study, you will see in this package, normally there are some pre-built algorithms or data models, and the organization's design logic is the same in scikit-learn, and I'm pretty sure that scikit-learn has richer module range than many other packages. And also, scikit-learn is only one package in Python among many others. For the next class, I will introduce you another one. But for now, let us consider the scikit-learn linear model and perceptron. Okay, that is a class. And to have a perceptron model, we need to get our perceptron to instantiate this class. Okay, so look, good. To train it, obviously we have learned. We know that there are stages. First stage, you need to let the model to see the data. Okay, and that is called training. And in scikit-learn, training is called fit. Fit the model to data. Okay. Oh, sorry. Fit. Let's say x 5 y 5. So what we get? Okay, we now have a perceptron with such and such trained parameters. Anyway, now we can use this perceptron to distinguish the data points. Let's see. Predict. Okay. See how this works. Now let's do toScatter and compare the ground truth labels and the prediction from the trained model. In the first figure, we do the scatter of the original data. In the second figure, we do the scattering of our prediction. And by scattering of the label and of the prediction, I mean we plot the same set of data points, the X part or the extract features, but color these features using different scheme. One scheme is to color the features using the ground truth label, and secondly, we will color the features using the predictions. Let's have a look. Oh, they look pretty similar to each other. I will assume there will be some misclassifications in the boundary areas. Have a look at here. And oh, sorry. How to do it again? Okay. Have a look at this area, and this area, the color scheme is different from this one, but the difference is minor. So we have get a model that classifies the data correctly in most cases. How the training works, we will learn in the class. Okay. And later in this video lecture, I will try to get I will try to sketch the training algorithm. What is going on under bonnet? But I have to warn you at this point that the previous analysis we have just seen is a little bit problematic. Why? Look at this. We fit the model, use this set of data, and we evaluate the model's performance using the model's prediction on the same training set of data. So by doing so, we can only verify that the training algorithm works, and we have a predictive model that seems learned the training data, but how the model generalized beyond the training data, how the model behaves for the data that hasn't been seen during the training stage, for that we haven't verified yet, and that will be done in our lab tutorial in the first week. Okay, perceptron is arguably the first artificial intelligence algorithm, and its construction is surprisingly simple. You combine the attribute of the data with constant weights and compare your combination with some threshold, and do the classification like that. The inspiration is of course from biological neurons. So the training of a perceptron is just the way of determining the width and the threshold. we have just seen that there are already implemented algorithms helps us to use such models to deal with practical data. Let's have a look at how the perception is applied to the data space. What I need to emphasize here is we are consider the space, which means every possible seen or unseen samples, not only the samples we have observed during the training time. If we have the two-dimensional data space, and now we have perception has two weights, because there are exactly the same number of weights and the attributes of each data sample. So actually, you might consider the perception model itself a point in the data space. Let's call it a virtual data sample of the perception model. Now, if we connect the origin of the data space to each of the points, including the virtual perception sample point, we can correspond each of the point with a direction in that two-dimensional space, as it is shown by this arrow in the figure in this slide. And that arrow shows a particular perception weight. And now the evaluation of a perception can be considered as to calculate the alignment of the directions corresponding to other points in the data space with the particular direction represented by the perception data point, perception virtual data point, or the weights. In this particular case, the weight has 1.0 in the x-coordinate and the 2.0 in the y-coordinate. So if we color the point in the data space with the alignment with that w vector, we can see that the gradient of the color corresponds to the w direction, and the color, the saturation of the color changes faster in the vertical direction than it is in the horizontal direction. This is another example. Now, the first element of w0 is 1, but the second element of w, that is w1, is 0. So now the evaluation of the perception changes only along with the first coordinate of the data sample, or the OX0, as shown in this plot. After calculating this alignment between the data points with W, the perception classifies data by thresholding. That means to draw a line on which of a particular alignment value. These two examples shows to use two different perceptions to classify the data samples. Remember that the thresholding and the bias, they are dependent with each other. You can change the threshold, but you can change the threshold but use a different bias, or vice versa. Generally, when we consider the perception classification model, we are more concerned with determining and studying the weight of the perception. You can consider the bias and the thresholds as second-class citizen in this model, because after you fixed a good set of weights, you can always easily find the proper bias or threshold to classify your data. Given the above geometric understanding of a perception, we can come up with a training algorithm for such model. Consider the case of classifying data into -1 and +1, which is another triviality of two-class classification, because whatever the label is, you can always relabel them into minus or plus. Okay, the algorithm works like that. If the current perceptron can classify all the training data correctly, then end. If there are misclassified samples, do the following steps for those misclassified samples. Say a sample is X, and consider if how it has been misclassified. If X should belong to the class of +1, and it is now misclassified as -1, which is the evaluation of the perceptron on X is less than the threshold. What we should do? We should increase the evaluation of the perceptron with X, and that is to increase the alignment of the perceptron's W direction with the X direction. How to do that? We can simply increase the vector W with X. That means to increase each element of the W vector with the corresponding element in that particular X sample. And if X has been misclassified in a different way, that is, X should belong to the minus class, but it is now classified to the plus class. That means the evaluation of W on X is beyond the threshold. We want to decrease the evaluation. What we will do? Simple. We decrease W using the value of the current misclassified X. And this is a very simple training loop. We do this loop until there is no misclassified sample left, and we finish the training. One impressive property of the sample training algorithm is that if there is such a W or a set of W which makes the perceptron classify the training data perfectly without making a single error, it is guaranteed that that training algorithm will find one of such optimal W. A sketch of the proof is like follows. If such kind of W exists, of course, we can take one of them and consider the particular one optimal W, call it W star. Apply the W star to all the training samples, and obviously, because W star is optimal without making any error, for the samples belong to the +1 class, the evaluation of W star on that sample should be a positive value, and if the sample belongs to the minus class, the evaluation of W star on that sample should be a negative value. So be it positive value or the negative value, if we multiply such value with the particular ground truth label y, -1 or +1, with that wx combination, we must arrive some positive value. You can think about that for a few moments, and that is true. Consider such a value for, I call that y flipped w applied value, whatever. It's a complicated name, but you can consider this. And all those values for all the samples are positive, and find the minimum one of them. In the above training algorithm, it is guaranteed the alignment of our particular W under training with the particular optimal W star. In each of the iteration, their alignment will increase at least of the minimal value of the previous discussed y flipped A value. This is a very brief sketch. You can find good reference to find this proof. But even you do not understand this proof, it is okay. You can just remember that when there is optimal W, that simple perception training algorithm will find the W. On the other hand, if there is no such error-free optimal W exists, the training algorithm may end up with flipping between one kind of error to another set of errors and will never stop. In practical usage, you must consider some stop condition of implementing that algorithm. Beyond perception, there are many more different kinds of linear models. You might be surprised on how such a simple learning scheme can achieve in practice, and how the seemingly trivial change of the learning goal and how to adapt the model, the learning step, and also how the meta training strategy, like how to change the training method during the training. Such kind of scheme can change the behavior of the model in practice. There are a few very good references I list in this slide. You may check. And in class, we will practice the training algorithm of perception. And in the lab tutorials, we will practice how to use the machine learning package to train the perception, which I think the implementation is much richer, much more complete than we can do it from scratch. And also the perception will have impressive development if you put many more, not only one perception, but multiple perceptions together, and you do one step of perception evaluation and take those output to put it into a second stage of a different set of perceptions, and do it again and again. You end up with multiple layers of perceptions. And that is a very hot and popular area of deep neural network learning. I may not talk about deep learning in the next lecture, but in the next lecture, we will consider how neural network works. Okay, this is for this week. Thank you for your time. See you in class.